Anybody have it? Number 5 for vibrations? Yeah, that's an old version. Each class I'll be updating that, you know. Yeah. Yes. It's a okay, you can so vibrations number 5. That's a rectangle like this, right? And a spring like this. Okay. And oh, okay. So this is not a thing. Up here, there's that. And what are the... Okay. 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 And we're just trying to come up with the solution. Okay. Okay, yeah, so we want theta as a function of time, and then the frequency, which if we get a, you know, F, AF, F that. Frequency. Okay. So, free body diagram. And actually, let's do a free body diagram in the... So we're going to do like a general one during its motion. There's going to be a force vector here that we don't know. At the center, there's going to be a weight force. And that is 98.1. And then there's going to be a spring force that's equal to 1000x. And so if this is the coordinate system, and x is positive, then the spring force would be that direction. So we don't need a negative there. And let's represent all of this in terms of an angular position. So, well, we're heading towards rotational Newton's second law. This is, you know, a rigid body problem, so let's calculate. I'm going to call this point A. So the moment of inertia about the point A is 1/12 times the mass of 10 times 0.5 squared plus 0.25 squared. And then it's not at the center, so you have to add on the parallel axis theorem part, so 10 times 0.25 squared. And what do you get for that? 0.885 kilogram meters squared. And then the pin at the top. And then this X value is the horizontal leg of this triangle. This length is 0.5. This is theta. So the component that we want is 0.5 times the sine of theta. And then since we're doing everything in terms of theta, we also need to represent x. Oh, that's what we just started doing. So that is the x value. So we can rewrite this as so we can redraw this free body diagram as force going this way of 1,000 times sine of theta. And then we also had, what? Yeah, 1,000 times 0.5. And then we have this force of 98.1, and then R. So let's write out this table: rho, force, moment. So first of all, the rho vector for R is 0. So that's not going to come up. And for the weight force, the rho vector is from the pin to the center of mass. So that is, we can think about that as this other triangle. So this is 0.25 sine of theta. This is 0.25 cosine of theta. This is 0.25. And so the rho vector for the weight force is 0.25 sine theta, negative 0.25 cosine theta. The force vector is 0, negative 98.1. And so that is negative 24.525 sine theta, right? And then we have the moment produced by that spring force. The rho vector for that is 0.5 sine theta, negative 0.5 cosine theta. The force is negative 500 sine theta. and then 0. And so you get negative 250 cosine theta sine theta. And so now rotational Newton's second law says negative 24.525 sine theta minus 250 cosine theta sine theta is equal to 0.885 alpha. And so 0.885 theta double dot plus 24.525 sine theta plus 250 cosine theta sine theta is equal to 0. And we're going to assume small angles, right? It says that in the problem. So right now we have a differential equation that you can solve numerically, but coming up with a closed solution would be a pain. So we can assume that if theta is small, sine theta is about equal to theta, and cosine theta is about equal to 1. So we can rewrite this as 0.885 theta double dot plus 274.525 theta is equal to 0. And then, so our differential equation says theta double dot plus, can someone divide that 274.525 divided by 0.885? Well, if you assume that that angle theta is small, I mean, I'm just talking about the cosine, you know, cosine of 0 is 1. And so if that angle theta stays small, then cosine of theta stays close to 1. .2 theta is equal to 0. And so theta is a function of time is equal to a times the sine of, what's square root of this? $17.6 plus phi. And then you can use the boundary conditions if they're given to solve for those constants. The natural frequency is 17.6. So the frequency is 1 over 2 pi times 17.6. And what's that? Any questions about that? So those small angle approximations are the first terms in the power series representing sine and cosine. Those are useful in a lot of things. A lot of times when you can see what the answer is, but you don't know how to get there, you can say you assume small angles and just throw a bunch of stuff away. Okay, that'll come in handy at the U for sure. Okay. Let's do another example. So let's say we have this big mass here attached to a relatively small, low mass bracket where this length is 0.2 meters. Yep. And let's say that this is 2 kilograms. This is 0.1 meters. And we have a spring going this way. And the pin is here. And the spring constant, let's say that that's 500 newtons per meter. And so we want theta as a function of time and the frequency. This pin here is attached to like a wall behind it or something. All right, well, and let's assume that this is at rest in this picture. So this picture shows equilibrium. And so that means that if we choose, so we're going to use sort of the same approach that we used when we had the hanging mass that was oscillating. Equilibrium, so this, in equilibrium, there's a force here, okay? And there's a weight here, and both of those are producing moments, okay? So it's not that there are no forces here, but the moments all balance out and it's in equilibrium. And so what we're going to do is say that this equilibrium position is like our zero angle. Okay, we're going to call that theta equals 0. And then we're just going to assume that by representing this position as our theta equals 0, we're going to treat this spring constant like it's 500 times whatever this is based on at 0 radians. And we're going to ignore the yeah, right. So we're going to ignore the weight here, okay? Because switching the 0 theta to this position here cancels out the weight. We could go through that whole derivation again, and you would see that it works. Exactly. It's exactly like that other example, but now it's angular. Okay. Otherwise, we would.
So why didn't we do this on example?
It was the weight wasn't producing a moment in that example. Okay. So, but this one, that weight is producing a moment, and it would. So if we wanted to express all the forces explicitly, we'd have to put the 0 position for this spring at the resting position of the spring, which is something shorter than is drawn here, and we'd have to put that weight in, and then we'd go through and stuff would cancel out. So instead, we're just going to put our 0 position to be at the equilibrium length of the spring and leave the weight out. The mass is still going to matter. Who's with me on that? Who's not with me on that? Everyone else is somewhere in the middle. Why don't you go through that derivation?
Yeah. Well, it's basically saying that if it's in equilibrium, the weight is pushing down and the spring is pushing back exactly how much force the weight is pushing down.
So
it's not, they cancel each other out. They're not
right.
valid anymore.
So let's.
But wasn't that the same case in the last problem? You just pulled the weight the other way.
The last problem, the difference was in the equilibrium position here, the weight is acting through the line of action is through the pin. So we didn't have to think about that or worry about that. So in this equilibrium position, that spring is at its resting length. In the one that we're doing now, the spring is not at its resting length at equilibrium. So why can we ignore the weight? Well, it's analogous to the hanging mass spring system. And the idea is just that when it's at equilibrium, you have a weight here that's equal to, what did I say, 2 kilograms? So this is 19.62. And this force is K, what's that, 500, times, let's say, so for this one we'll do x equals 0 at the resting length, not the equilibrium length. So this moment is x sub 0, or this force is 500 times x sub 0, where x sub 0 is x at the equilibrium position. Then we have this that's not going to produce a moment. And we have to think about the sign of that too. If you have a positive value of x, it's going to go the other way. So we need a negative here. And then rotational Newton's second law at equilibrium says, so this is a counterclockwise moment of 0.2 times 19.62. This is a clockwise moment of 0.1 times 500 x0. And these are equal to 0 because it's at equilibrium. And so x sub 0 is equal to, well, you can get a value for that. Maybe I should have left this as, let's write this as negative kx0. This is mg. And let's make call this length L1 and this length L2. Just so it's a little more general. Okay, so at equilibrium, we have the counterclockwise moment of L1 mg and the clockwise moment of L2 kx0. And so x sub 0 is well, a negative here is the same thing as that being positive going this way. So if that force pushes back that way, it would be a clockwise moment. So you got L1 mg over L2 k. And if you make that substitution into the general case, all right, so now in the general case, we have I wish I would have done this a little different. So in the general case, we have L1 mg minus L2 times this stuff. This comes out to be just, when you cancel stuff out, this comes out to be L1 mg, right? Is equal to L2, yeah. L2K. No, the L2 cancels the L2. Those two on the bottom cancel. Yeah, that's true. So what am I trying to do here? That's right. And we are doing, yeah, I alpha. So we get 0 is equal to I alpha. So what? I just substituted x naught into the top one. Oh, well, except now I did the general case where it's in motion. Okay, let's do this. This is, sorry. Well, you can start over on another page, but I'm gonna choose a different. Okay, so I'm gonna choose a different 0 position. So I'm gonna choose the 0 position at the equilibrium position. X equals 0 at the equilibrium position. Okay. Well, we found out that, yeah.
We learned not to do it that way.
That's right. We learned not to do it that way. Exactly. So at equilibrium, this is a free body diagram at equilibrium. And we can write this as, okay, so the force at equilibrium is K times 0 minus x sub 0, where x sub 0 is the position at the spring's resting length. Nope, negative. Okay, so free body diagram at equilibrium. So do you see why? So if our zero is at, I think this is the way I did it with the K mass 2. If our zero is at the equilibrium position, not at the spring's resting length position, then this is going to be producing a force when the whole thing is at equilibrium. Okay. It's going to, and that force is going to depend on the distance from the equilibrium position to the resting length. Okay. So free body diagram and equilibrium. I had my zero position at the spring's resting length, not at the equilibrium position. So I think this is going to make the algebra come out simpler. That is a free body diagram. I want to do rotational second law. Okay, so we have L1 mg minus k times negative x. So this is plus k x0 is equal to 0. And there's also an L2 there at the moment. And so the moment produced by the weight is this, and that's always going to be the case. And it's equal to negative L2 k x sub 0. Okay, so now we're going to go to the general case. So we have the weight acting down. And now in general, we have this force of negative k times the quantity x minus x sub 0. And rotational Newton's second law says that that L1 mg minus kx plus kx0 is equal to I alpha. Yes, L2s on both of these. But L1 mg is equal to this. And so it just comes out to be negative L2 k x2 is equal to I alpha. And the result is kx, yeah. The red thing starts at the result we got from equilibrium related that moment produced by the weight to this expression. And if you substitute that expression in for the moment produced by the weight in the general case, you get this expression where the moment produced by gravity is accounted for by calculating the spring force with the zero at the equilibrium position. Okay, any questions about that? So the stuff starting here, forget all the stuff I erased and went back and whatever. If you start here, this all makes sense. Well, this is when theta is 0. So all I did so far is I showed why you can, so in any case where the weight pulls this thing to an equilibrium position where some spring is at a deformed length, okay? Like in this example, the weight's making the spring fight against it to hold it in equilibrium position. Normally you choose the spring's resting length to be your 0 because the spring force depends on how far the thing is from resting length. But if instead you just put your 0x to be at the equilibrium position, that sort of inside that calculation deals with the weight, and you just don't have to include it. So we did an example like that last class where we drew the free body diagram as if there was no weight in it because it was accounted for by the spring force that dealt with the weight. Okay, so what's the problem we're doing? Okay, so we want to calculate theta as a function of time. So free body diagram. Mm-hmm. Yeah, that's right. So with x equals 0, the equilibrium position, and we have to come up with an expression for the moment of inertia of this thing. Okay, so we have this force here, R. So I guess, so yes, we've basically done it. So why don't we just make the couple of little patches to go from what we have to this? What I'm trying to do here is, so the last thing was to motivate this idea that you can approach all these problems without the weight in them at all if you choose your x equals 0 to be right. And now I just want to show the steps for how you do a problem like this from the start. You know, it's not going to take a lot of extra time or anything, but that's why I'm not just working from what we have. Okay, and then spring force is negative 500 x. Yes. Yeah. If you have a positive x, it moves this way, and then the spring, it compresses the spring, and so the spring pushes back on it.
That arrow drawing is really confusing people.
Yeah, well, you know, that's how I do it. There's some things that, like, I do it this way, and I'm convinced you should do it this way. This isn't one of those things, but if you don't like that, you might just have to think of your own way, you know, like, I think you just need to come up with a way that makes sense to you. It's not really a complicated concept, but every time I say it in words, it sounds complicated, you know what I mean? Okay, and now we need to represent moment of inertia of this system. So if this is A, what's the moment of inertia about A? How do we calculate that? We're assuming that 2 kilograms is the only mass that's not negligible. Everything else we're ignoring. Yeah, well then the spring's resting length for this problem to be set up to be right would just have to be very, very close to that equilibrium position, you know. I mean, we're just saying that whatever the stiffness of the spring is, it's just enough so the equilibrium position of this thing is at that vertical horizontal position. Okay, well, the definition of mass moment of inertia is the integral of rho squared dm. We only have one dm, it's that 2 kilogram weight. So this is just equal to 2 kilograms times 0.2 squared. And so that is 0.08 kilogram meter squared, right? So now we can go to the rotational equation. We're treating this like there's no weight. So the only moment is going to be produced by a moment arm of 0.1, a force. It has mass, but we're not considering the weight force because that force is included in the spring force the way we've written it. Actually, and not really the force in this case because it's rotational. The moment produced by that weight is included in the moment of the spring, the way that, you know, exerted by the spring, the way we've written it. This is for this. So what this is saying is that the force direction is that way with a magnitude of 500x. So magnitude of 500x times this, it's rotating clockwise, so that's negative. And this is all equal to 0.08 alpha. Now we're going to have to represent that x in terms of theta. So x is equal to 0.1 times the sine of theta. So we have negative 0.01 times 500 sine theta is equal to 0.08 alpha. And so this says 0.08 theta double dot plus 5 sine theta Yeah, I skipped a step. And then this is equal to 0. So what's 5 divided by 0.08? 62.5 sine theta is equal to 0. Okay, so that's the correct general equation, but if theta is small, we can write the one that we know how to solve, and that is theta double dot plus 62.5 theta is equal to 0. What's the square root of 62.5? What did you say? 7.906. And so theta as a function of time is equal to A times the sine of the quantity, 7.906 E plus phi. Use the boundary conditions to find those. And then the frequency is 1 over 2 pi times 7.906. What's that? What? 1.26 hertz. Any questions about that? So let's summarize where the confusion was and where it wasn't. So the confusing part was when I was trying to set up an expression to figure out what moment was produced by gravity. Okay, and to see that it's easy to cancel that out. And I had a false start and then went away where we finally saw it, But all that was just to show that in general, if you have a problem with weight in it, you can just change where your x equals 0 is to the equilibrium position and get weight out of the problem. That doesn't get mass out of the problem, that just gets the force applied by gravity out of the problem. And this is the second example we've done like that. This is the rotational one. We also did the translational one that was a spring in a vertical position.